In the second lecture on accelerator techniques, we shall discuss on linear accelerators, otherwise known as LINAC. In linear accelerators, the particles are charged in steady steps. Alvarez et al. In 1945 accelerated the protons to 32 MeV using LINACs. The linear accelerator works on the principle that under an alternating electric field, the particle is accelerated during the positive half cycle and retarded during negative half cycle. As shown in this figure, a linear accelerator consists of cylindrical metallic tubes which are denoted from 1 to n. Their axes are along the straight line. And as you can see from this figure, the length of the cylinders is increasing. That is, the first cylinder is shortest, second is of length larger than the first, and the third cylinder is larger in length than the second, and so on. And all the cylinders are connected to one terminal, and even cylinders are connected to other terminal. Both terminals are then connected to high frequency oscillator of almost 10⁻⁷ Hz frequency. And these cylinders are kept inside evacuated glass chamber. When one set of cylinders get negative, then the second set of cylinders is positive. In the next half cycle, the polarity is reversed and the beam of ions enter the tube along the axis. When the ions enter the tube, the ions are accelerated during their transit across the gap between the cylinders. That is, the ions are accelerated in these spaces between the cylinders. Each tube has constant potential, hence electrons cannot be accelerated within these tubes. If positive charge Q enters the accelerator such that first cylinder is positive, then the second cylinder will be negative. The positive ion will get accelerated in between the gap of first and the second cylinder. The accelerated ion will now travel through second cylinder with speed faster than it had during traveling through the first cylinder. As the length of second cylinder is longer, hence the ion will reach in the same time to reach in between the gap between second and third cylinder. In the meantime, the polarity gets reversed, that is, the second cylinder will become positive and third will become negative. The ion will again get accelerated in between the gap between second and third cylinder. To keep the ions in phase, the cylinders are made longer in order to compensate for the increasing speed of electrons, that is T equal to cylinder length over speed of ion, which is equal to constant. Here T is the time of travel inside a cylinder. Hence, after passing through every gap, the ion gets accelerated. While moving inside the tube, which is at a constant potential, the ion moves at constant velocity. Theoretically, we can conclude as follows. Let charge Q have mass m and V is the potential difference between successive tubes. The velocity of charge while entering the nth cylinder is Vn. Then the kinetic energy of the ion inside the tube is half mvn square. The energy picked up by ion after passing through the cylinder is Q times V. For n such gaps, the energy is n times QV. Hence, we can equate these equations and write nQV equal to half mVn square. From this, we can find the velocity of the ions inside the tube to be Vn equal to square root of 2nqV over m. Of course, this equation will fail for relativistic velocities, that is, when the velocity of the ion becomes equal to velocity of light. Earlier, linear accelerators were used to accelerate the protons only, but these days electrons can also be accelerated. LINACs provide a very well collimated beam of charged particles, and their drawback is their large length, due to which more number of cylinders are required.